I love to 3D print all manner of electromechanical projects, and one component that 3D printing has completely revolutionized is the humble gear. Finding the right gear to buy off the shelf used to be a huge pain, but with 3D printing, you can create any size gear you want and have it ready to use in a matter of hours. But have you ever wondered, just how strong are they? And what material, print settings, or tooth profile is best? To find out, I built this. In this video, I'll show you how I built it, how it combines 100-year-old technology with state-of-the-art motor controllers, and how it absolutely annihilates 3D printed gears. For science, let's get started. How's it going, guys? Angus here from Muse, where it's my aim to empower your creativity through technology, and this thing has been a long time coming. I've always been curious about the strength of 3D printed parts when it comes to practical, real-world projects, and gears are one of those components where strength and longevity really matters. A few years back, I conducted an experiment to find out how much static load 3D printed gears could take in a range of materials using a torque wrench to stress them. And I tried materials from PLA to PETG, ABS, and carbon fiber nylon. And while this test yielded some interesting information, by far the biggest criticism was, hey, this isn't really a fair representation of how the gears would actually wear during use. And you know what? I completely agree. Gears roll against one another at high speed, transferring torque during use. They don't just sit static, holding out against a load until failure. And for literal years, I sat on this problem trying to figure out just how to simulate this actual use in a way that was repeatable and yielded real usable data. And I think I finally cracked it. The plan is to create a test setup with the gears being driven at a constant RPM for a precise, repeatable amount of time, and for these gears to be loaded by a simulated load. Something that simulates the resistance of, let's say, a robot drivetrain as it propels the platform around. I'll then increase the speed and load until something fails, and then rinse and repeat for a range of 3D printed materials to find out once and for all what filament makes the best 3D printed gears. But anyway, that's the plan, so let's go over all the parts, starting with the key element that makes this project possible, the ODrive S1 and their 100 kV outrunner. I got this bit of kit from Oscar, the designer of the ODrive, way back at the first open source in San Francisco, and it has quite the impressive feature set. Unlike the brushless speed controllers I'm used to for powering my combat robots, the S1 has a raft of features for controlling BLDC motors with precision and accuracy. You can precisely control position, torque, and velocity, changing all of these parameters on the fly using Python script or over USB, all while reading out useful information through a graphical interface. It is probably completely overkill for my use case, but it will allow me to drive the gear train at a precise predetermined revolution per second and spit out all of that juicy data as the gears struggle to survive. The second half of the equation is the load, and this took longer than I thought to figure out because it turns out that simulating this kind of load is a rabbit hole in itself. In effect, I'm building a dynamometer or dyno, and in my research, I discovered that developing torque can be done in quite a few number of ways. Some basic setups literally rub something with a lot of friction against the output. Others will use hydraulics principles to either pump fluid through a restrictive loop, or even spin paddles in a large pool of liquid. But the method I really liked was to use electromagnetism to create a load on the system using a principle known as back EMF. Without going too heavy into the details because I wouldn't call myself an expert, a basic motor creates rotation when you provide power by energizing coils which magnetically repel or attract magnets, which spins the assembly. However, did you know you can flip all of this around, turning the shaft of the motor instead to output a voltage, effectively turning a motor into a generator, and you can do this with pretty much any motor. But if you short the output wires instead, and then trying to turn the shaft, it actually becomes harder and harder to turn the faster you go. And this is due to a phenomenon called back EMF. This voltage that the motor generates is actually in opposition to the direction you're rotating the shaft to create it, which effectively makes the motor fight itself. The faster you try to turn the shaft, the more back EMF is generated, and it becomes harder and harder to turn. This is actually a really useful principle if you want to slow down from speed, because it's proportional to the speed of the motor, going from a really high braking force to nothing, as you slow down, and it's used in all manner of things from electric cars, trains, and even to slow down roller coasters. It won't slow you down to zero, you still need to use conventional braking methods for that last little bit, but for my use case, I actually want to stress the gears at speed, so using back EMF as a load seems ideal. And the motor I've chosen for that is this monster, a 200 watt scooter motor. This bad boy was the ideal choice for electric scooters 20 years ago. Nowadays though, it's ancient technology. Check this out, this motor is 3 kilowatts. That's 15 times more powerful, and it's a third of the size. However, this old motor is bulletproof, and I love being able to reuse all my old parts again, so I think it'll make the perfect simulated load for the gear tester. However, just in case the back EMF generated is too much load, I also bought this monstrosity. This is known as a rheostat, or variable power resistor. It's an old, outdated way of controlling current by literally burning away excess energy as heat. This linear rheostat has a variable resistance of 0 up to 1000 ohms with a continuous rating of 300 watts, although in hindsight I probably should have gotten with a much smaller range, maybe 0 to 10 ohms, but either way, combining this with the analog voltage and amperage gauges, you should be able to dial in the exact amount of rotational resistance needed from the scooter motor to appropriately load up the gears. Now we're going to need a really heavy duty testing rig to constrain all of these parts, so I designed this up in Fusion. It uses chunky aluminium plates and mounting brackets to constrain everything exactly where it needs to be, and thanks to this video's sponsor, PCBWay, they turned out amazing. You've heard me say it before, PCBWay is your one-stop shop for all things fabrication. You can get custom PCBs, 3D prints in a huge range of industrial materials, and of course, CNC services. These big plates were machined out of 6061 aluminium and look amazing as is, but if you wanted, you could also add custom finishes such as anodizing, powder coating, and bead blasting. As you would expect, all of the parts are of high tolerance and fit together perfectly, so why not give PCBWay a go for your projects? You can use code PCBWay MakersMuse10 to get $10 off any order of $30 or more, and you can find more information in the description below. Originally, I had planned to run 2 huge gears between the motor and load, but during assembly, I realized just how big those gears would be, which could be a problem if I wanted to test them out of challenging to print materials like PA12 or polycarbonate. So I modified the design to have this smaller center gear, which I'm hopeful will also result in a gear with a higher duty cycle than the rest. That is, the teeth experience more wear because they come into contact with the other gear teeth more often, but we'll see if that actually holds true in testing. These modified parts are printed in PETG-CF from Peopoly, and they should be more than strong enough for initial testing, but again, once the design is finalized, I'll definitely be upgrading them to metal through PCBWay as well. Alrighty, it's time to spin up some gears with the O drive. The S1 connects via USB, and once you set it up correctly and run the calibration routine, it can be controlled precisely through the GUI or by running Python script. Again, I'm still working on the Python script part, but I did throw together this simple script which ramps velocity up from 5 to 10 to 15 rotations per second every 5 seconds. There will be plenty more programming to come once the actual testing starts, but for now, I'm stoked with the results. And here we are, after months of design, fabrication, programming, and building, it's finally complete. This is the Gear Annihilation and Testing Rig. I'll be using this bad boy to test all manner of printed gears to destruction ranging from different materials, print settings, tooth profiles, and more. But I need your help to do it. Let me know in the comments below what tests you want to see and what data is important to you. Is it long-term wear at low loads, or is it short-term use under high loads, or something else entirely? I'll choose the top rated comment and run with that for the next video in this series, but for now I've printed these mod 1.5 gears from PLA at default settings to break it in, literally. Well, that was unexpected. The D-bore on the driven gear deformed and spun before the gears themselves failed. This is actually a super common problem in combat robots, so it's pretty useful data already, but I want exploded gears. So for now, I reduced their thickness down from 10 to 5 millimeters, and I'm not playing around anymore. It's time to go full resistance at 900 RPM. Oh boy. Got that sweet smell of PLA, melted PLA in the air. Yeah, that did exactly as intended. And now it's melted. Now it's melted in place. Awesome. If you enjoyed this video, then you'll love this build where I 3D printed a supersized PC fan using a motor even more powerful than this one, and I tested it out against all sorts of things. Thanks for watching, guys. Bye.